So let me introduce the next keynote speaker, Dr. Naveen Verma. Dr. Verma is the professor and director of Keller Center for Innovation in Engineering Education, Princeton University, and he is also the CEO and co-founder of NLarge AI. Dr. Verma earned his PhD in advanced computing and integrating circuits from MIT, and the title of his talk is Bridging Fundamental Research to Industry Innovation, America's Unique Advantage. And welcome, Dr. Verma. Thank you.
All right, thank you very much for the opportunity to talk to you. It's been a day really of a lot of excitement, and I hope I can continue that sentiment in the topic that I want to talk about. I think we all know, I think we all believe with a very high level of conviction that America has been an innovation juggernaut. And I think it's very easy to make that argument. It's very evident in everything that we do and have been involved in. I think that innovation comes, thankfully, from a number of very critical different corners and aspects of our country and our ecosystem. And so I just want to talk a little bit more about that. And I want to bring a perspective in particular from one of those corners, which is fundamental research that I've been deeply involved in, and talk a little bit about how it's so important and why it's so important. I think that this particular category comes as a topic we need to focus on first and foremost because of its need, but secondly also because of a very concerted spirit, and then third, of course, because of a unique opportunity that we have to bring this together into this ecosystem through Netcast and the programs that are being championed here. Let me see if I can proceed. Here we go. It turns out that in my research, I focus on advanced computers, and that's focused a lot on AI. There's a story that this chart tells that gets me as a researcher very excited. It talks about a two-sided challenge. The first, the one on the left here, talks about the massive explosion that we've seen in the amount of compute that's needed for AI, something like a 10,000x factor over about a decade. Unprecedented. We've never seen it, never had to deal with it, even in the best of times of Moore's Law. The one on the right talks about a slightly different challenge, which is that not only do we need a lot of compute, but we're doing that on immense amounts of data. And of course, it now turns out that data movement and accessing things many of us have talked about also becomes a challenge by the same 10,000x factor over a 10-year run. The fact that we have these kinds of explosions and the technical challenges they pose are very exciting to me as a researcher in this space. But this is not what I want to talk about. What I want to talk about, I'll come back to, of course, the technical challenges, but I want to do that in the context of a slightly different story that this tells in terms of innovation. The first is, what we can see as a result of this explosion is that we truly need transformative and differentiated solutions going forward. And we need to think about where those are going to come from and how those origins are going to get connected to the rest of the ecosystem. That's thing one. Thing two is that the reason we've had this explosion or a 10-year run is because of the ways that innovation in the ecosystem has been enabled. So yes, we need these transformative ideas and solutions, but we also need those to be embedded and blended and accessible to the ecosystem so that this kind of thing can continue to happen. So the opportunity here is to talk about both what the sources of some of these differentiated solutions are going to be, but also the pathways by which they'll be integrated into the ecosystems so that we can innovate in these ways going forward. At least three spheres that I want to talk about here. They include fundamental research. As you'll hear from me, I believe that fundamental research will be a critical source of really differentiated and transformative ideas. It's where we'll have some basic breakthroughs. It's also where we'll have glorious failures. Okay. The other one here is what I broadly call innovation ecosystems. These are the ecosystems that are bringing transformative new products and transitioning those into the markets and into the broad use. These are startups. These are various kinds of industrial and government research labs and so on. They're tasked with building and risky platforms and products. And then, of course, the third is industrial leadership. This is the category that, with brutal consistency, needs to be able to deliver platforms and products that continue to advance so that we can see those kinds of innovations that we've seen. I believe it's very easy to make an argument that in each of these three areas, America is the best in the world. Okay? There's plenty of aspects where many of our peer countries are being aggressive and so on and so forth, but these three areas are ones where we have a unique and unparalleled advantage. I think it's very important for us to think about how they come together to address some of those innovation needs that I talked about on that previous slide. And some of these have been greatly connected so far. In fact, I would say all three of them have to various extents been very well connected. Innovation ecosystems and industrial leadership, we've seen great onboarding of innovative technologies into large incumbent companies that are delivering products to the ecosystem. Fundamental research has also had successful models. I believe that we are operating, though, at a level that's disproportionately small compared to our potential. And so I think it's important for us, with the opportunities we have here in programs and structures like Netcast, to think about how we can amplify that and bring it to real fruition. So I want to talk with a little bit more fidelity about each of these. And I also want to talk in particular about some of the impedance mismatches from some of my own experiences. Just a little bit more on these spheres of innovation. The first, fundamental research. Like I said, this is really a place where we have opportunities to think about basic breakthroughs and where there will be failures. One of the reasons that I'll keep coming back to for why we'll have failures is because the systems we need to build and deliver to the ecosystem are very complex. So even if you have a fundamental innovation at some technological level, putting that in place into the systems that are actually needed to leverage that is a challenging and risky thing. One of the real advantages we have, though, here is that we have the time and space to think about fundamentals, to think about fundamental limits. If we were to invest in some basic technology, which very likely we won't get right in the first iteration because these are complex things, is it worth it for us to continue to invest in it? Where will it end up if we do? Thinking on a fundamental level like that allows us to think about where to put our investments and efforts. This is pre- and non-competitive, as I'll talk about, which is an advantage. In terms of innovation ecosystems, these are now these structures which can deliver not generational products that are kind of having incremental improvements, which I think you can say perhaps is something that the industrial leadership is tasked with. These are places where we can have real step changes in capability. One of the things you'll hear me talk about here is that it's important to focus on emerging use cases. If there's ever an opportunity for an incumbent solution to address a use case, an incumbent solution probably should address the use case. But the real opportunities here are what gets unlocked by some of these disruptive solutions and what challenges that poses. And then, of course, there's industrial leadership. As I mentioned, this needs to deliver platforms with predictability so that the entire ecosystem that's innovating knows where things are heading and can rely on these platforms. This, of course, making real platforms available to the ecosystem requires massive investments, and that has its own challenges. I want to talk about how each of these has an important role and to contribute to innovation. But what I also want to talk about is that while each of them is a sort of distinct sphere, in fact, the handoffs between them are not clean. And so what we do need to think about is how to create sustaining and integrative structures for innovation, and of course, the opportunity that we have to do that with organizations like Netcast. Okay, I want to come back to something that I researched just so that I can use it as an example to point to specific challenges. Turns out that I've been very interested in a technology called in-memory computing, and I think it's been mentioned. It's regarded in many ways as a holy grail technology for addressing some of the challenges in AI compute. You remember from that first slide, I talked about this two-sided challenge, massive amount of compute, but also data movement. This is one of the unique technologies that has the potential to address it. How does it do that? Well, if you look at traditional digital architectures, the prevailing architecture we've had for 75 years, the von Neumann architecture, separates memory and compute. And when you do that, you have this massive amount of data, because of course, remember, the size of our AI models is exploding, and so the size of these memories explodes. But now you have a cost of moving data from the point of storage to the point of communication, to the point of computation, rather, and that can be an enormous cost. Now, of course, once you've done that, you also need to compute that data or process that data. And the truth is, if you're using digital technologies, it's a particular fundamental technology, you can do as well as you can do, and depending on what the attributes and node of that technology is, we can sort of get a read on what the energy efficiency is going to be. In-memory computing is a little bit different. In particular, in many forms, it relies on analog computing to break through some of the barriers of that energy efficiency. But also, it can solve the data movement problem. It turns out, by dumb luck, a lot of the compute we have to do in AI is matrix multiplies, and it turns out that that involves a big parallel operation. You got multiplies and multiplies and multiplies between elements, but it also involves a big reduction operation. You do an accumulate along the inner dimension of a matrix. That gives you the chance to reduce all of this data within the memory so that all you're communicating out is one result. Sounds good. The problem is you're not accessing bits anymore, ones and zeros. You're accessing this accumulation result, and that has many levels. And this introduces an S&R trade-off because you now need to be able to reliably decipher all of those levels. Okay, so this is a basic framing of this technology. Let's move on from this. But what I do want to point out is these basic trade-offs has given us a lot of clarity in fundamental research that's allowed us to think about innovation. I had the good fortune to talk to a lot of industrial companies. All of the big AI companies, many of whom are represented here, have explored this technology because of its potential, but they've been confused. And this is an aspect that fundamental research can really contribute to. There's been all sorts of devices, MRAM and RRAM and SRAM. Which ones work? Which ones don't work? But by understanding the fundamentals here, that this is all eventually going to come down to S&R as an example, we can start to invalidate various technologies because they just don't have the signal-to-noise ratio. This is non-competitive. This is thinking at the fundamental level of what's required for these innovations, which fundamental research can do. Also has the benefit of being pre-competitive. In fundamental research, we can collaborate. In this case, we've had the good fortune of collaborating with the CTO's offices at TSMC, where we can build these systems and understand these various trade-offs. And what this does is it leads to some very counterintuitive solutions. We've built chips using some of these memory technologies that are being considered and found that they're enormously noisy and they're never going to work if you try to actually integrate them. On the other hand, what we can also see is that there's techniques that actually don't behave like memory is a high-precision analog problem. And we should build these systems more the way that folks at TI or ADI build 20-bit ADCs. So it's a very different way of thinking about these problems that gives us these breakthrough opportunities. But there's challenges. This all sounds good. Research in academia, unfortunately, can very often be biased. And the reason here is that we're not necessarily driven by incentives to solve those real-world problems. That's changing. You've seen many of my academic colleagues who are really inspired by solving problems. So I see this as a promising direction for change. But there's another challenge, which is that by not being focused on problems in the real world, full systems, drive us outside of our silos. We know that this technology needs to work with memory, needs to work with compute, needs to work with software, and that allows us to break what in academia are traditional disciplinary. If you're in the space, people spend entire careers devoted not just to a device, but a particular material system. And so breaking through some of these barriers is going to be really critical as we think about engaging fundamental research in these kinds of ecosystems we're talking about today. I want to talk a little bit about the handoff, moving from fundamental research to the innovation ecosystems. And here's the challenge. These innovations very often are not a silver bullet. They don't make everything better in every single way. And the reason for that is not because the innovations aren't good enough. The reason for that is that our systems today are so complex. And so when you start to insert these innovations in these systems, you naturally have these trade-offs emerge. And in the case of in-memory computing, there's this broad misconception that all of the memory balls and bottlenecks get solved. The truth is they don't, because of the ways that we have to now couple compute resources and storage resources. But in order to optimize systems, we actually need to break that coupling. That introduces all sorts of trade-offs and how these technologies need to work with other memory systems, so on and so forth. Now, what that means is, if you're innovating and starting to think about the handoff, we really need to start thinking about real use cases in the real world. And as you'll also hear from me, and I'll reinforce, we need to think about emerging use cases, because otherwise it's very hard to support the existing use cases in all of their maturity with all of the features that they need. An interesting question that I asked myself as we were thinking about spinning out EnCharge from the lab is, what is the line to draw? Academic environment is a great place to de-risk systems. And I think there's a perspective that you should draw the line where complexity becomes too big, because academia and fundamental research is not great at dealing with complexity. I would argue that's not true. There's nothing fundamental that prevents us from dealing with complexity, and I think we should empower, through the kinds of programs we're talking about here, be able to do more and more de-risking relative to the complexities that we have in systems. I think that's not the fundamental issue. The fundamental issue, I believe, is that at some point these complex systems need to be designed for use cases, emerging use cases. That requires working with industrial partners, and that's where there's a fundamental line to be drawn. Once again, it's a blurry line, not a bright line, because these systems, as we're optimizing them for those use cases, mean that we're playing with these trade-offs. Remember, these are not silver bullet technologies, they're just opening up new trade spaces. And so we'll still have residual risks with these new technologies as we try to target them to those use cases. So we want to leverage this fundamental research for de-risking complex systems, but there's this challenge of being able to do it to the point of where we start aligning to real customer roadmaps. This is no longer a fundamental research enterprise. Okay, let's talk about now the transition into that innovation ecosystem. And the biggest challenge, we might as well talk about it, we all know about it, is the massive capital cost that it takes to deliver, in particular, semiconductor products. You guys have seen these charts before, and so I'm going to reference it and move on quickly to say, you know, people often ask, if you've spent a lot of time de-risking these technologies in academia, does that mean that you can lower the capital cost of bringing these products to market? And the answer is, not even a little bit. At the end of the day, this is the cost that it takes to build something that somebody can use, starting from a fundamental innovation. You're not going to overcome this. So what to do about this? Well, there's not a whole lot you can do about this. This is where we do need support and real ideas. One thing I will say here is that as investment in semiconductors has increased, there's been investments in a number of technologies that we in the fundamental research community know have underlying barriers and should probably never have been invested in. Now, I talked to a lot of VCs, bless their hearts, but many of them don't know the work that's been done in the fundamental research sphere that might indicate which of these technologies make sense to invest in and which ones don't. In addition to being a source for innovation, I think fundamental researchers need to step up and engage in providing the advice or advising to these sorts of investors in the innovation ecosystem so that they can have a perspective of where some of these technologies can work and can't work. So this cost of delivering complete systems is unavoidable. In fact, you even have the residual risk of these emerging use cases that we now need to align to. But helping where these investments should be directed is something that fundamental research can do. We have a lot of perspectives in fundamental research that I feel are not shared or properly transferred to some of the investment community. Okay, let's talk about the handoff now from the innovation ecosystem to industrial leadership. And here's the challenge. If you look at the platforms that are supporting these ecosystems, many of these ecosystems, for the length of time they've been supported, have become extremely mature. And the technologies and platforms that are needed are equally complex. A lot of AI thus far has been done in the data center, and this is an example of a state-of-the-art data center processor. Many of us know about it. Look how complicated it is. We've got a reticle-sized compute chip. We've got 5 or 6 stacks of HBM. We've got high-speed networking surrounding this, and I haven't even gotten to the software. Okay? So for a new company, a new startup, to think about being able to displace this is not really very hopeful. Now, what we do have, though, are all of these emerging use cases. What we saw as we started to now think about deploying AI at scale in the data center is that the data center was actually very costly. The data center had all sorts of privacy and security concerns, and that drove this new sphere or this new approach to AI, which was to move it into the edge, into client devices, things like AI PCs. Well, these are interesting devices, and as the ecosystems around these are maturing, new technologies have the right to mature with them, and so they can be useful in driving these ecosystems. You don't need all of these features around a product like this. This is a case where you have a very concentrated need in a very fundamental requirement, which is energy efficiency. Our laptops are battery powered. And so this is the kind of place where new and emerging use cases can really help drive the innovation ecosystem forward. The challenges here are, of course, that the players in that innovation ecosystem, startups, need to now engage with the early stage markets and the ecosystems. And that's challenging because it's really the incumbents who are driving a lot of the ecosystems. And so forming the right partnerships, I think that was mentioned in the last panel as well, is really a critical requirement and activity that I think we can think about ways that organizations like Netcast can help with. I think the other challenge here is that your growth partners, for example, your VC, need to understand the fundamental technologies, so these early use cases. You need to be able to underwrite the risk, not just in the innovation, but also in these new markets and use cases that are emerging. So once again, there's a real challenge here in how we think about investment and success here. Okay, I want to talk about industrial leadership. Now, I talked about industrial leadership as having to brutally support the advances of the ecosystem, and because of that, having to be confined to incremental generational improvements on a technology level. That doesn't mean that the breakthroughs that industrial leadership has delivered haven't been enormous. You heard from Mark at the beginning of this session about the kinds of innovations we've seen from companies like AMD. I'm just using one example here. This is a talk that was given by Bill Dolly from NVIDIA that shows the kind of incredible progress that's been made by NVIDIA while supporting an ecosystem very proactively. What's really exciting here, and what American companies do extremely well, is that embedded in the ecosystems, they think broadly about how to engage with the ecosystem. Mark just talked about this as well. You're talking to the government, you're talking to users. In this case, you're talking to people who develop algorithms for AI. And in fact, the biggest advances come not from the hardware, but from new number representations, which are enabled by algorithms, or new forms of sparsity, which are enabled by new kinds of algorithms. And so being embedded in these ecosystems, supporting them, has allowed these leaders in America to, in fact, have really formidable advances. Of course, this takes us to the point where you're eventually going to hit some limits. Okay? The latest processor by NVIDIA uses a 4-bit number format. It's not clear that we'll be able to continue to push beyond that. Once again, the progress has come by pushing on those algorithmic aspects, but also the hardware, to the point where now we can start to see and we start to hear about all sorts of yield issues at the compute die and at the memory die and so on. So ultimately, the progress here is going to saturate, and we do need those fundamental and basic transformations that can set us on new trajectories. Okay, so I've talked a little bit about some of the challenges, and I hope that we'll continue to talk about them. I'll certainly be available for anybody who's interested. I also want to lay the seeds for some of the potential solutions here. And what I want to talk about first is, with the importance of fundamental research, how we can engage fundamental researchers. They have a very different culture, they have a very different set of incentives, but that also means that we should think broadly about the pathways for engaging them. And there's some great examples here. There's an innovator here who's deeply involved in Netcast, who back in the early 90s was one of the pioneers for low voltage. Today, if you look at that NVIDIA processor, it's running at extremely low voltages. That's one of the ways that it achieves that energy efficiency. In this researcher's case, this was done by an engagement between the research lab and industrial research groups and product groups. Here's an innovation by another researcher who's deeply engaged in Netcast. In this researcher's case, he felt like in order to introduce materials and devices innovations, he had to go and sit inside the organization at TSMC, where he could see the fab lines and see where these innovations could intersect them. So it's a different model for engaging the innovators. And then, of course, I've already talked about startups introducing new and disruptive kinds of technologies that get spun out of research labs. The other aspect I want to talk about is having trusted industrial insiders as innovation advisors and champions. We've got great examples of this. I think as we think about how to facilitate innovation from fundamental research and innovation ecosystems into industrial leadership, I think we should think about how to engage folks like this. These are folks who relentlessly wake up in the morning thinking about understanding fundamental research and understanding where within their organizations it can play a role, fighting against the barriers of having to deliver products, fighting against the barriers of not invented here syndrome, and so on. We've got great examples of folks like this who I think we need to strengthen our relationships with going forward and engage more going forward. The other is engaging emerging use cases. Someone's talked about you need to skate to where the puck is heading and not where it was. That's so critical with innovation because, like I said, you otherwise have this extremely steep hill to climb in terms of features that need to be delivered in products. So who are the folks in the industrial sector and segments that we should be engaging with? We've got an extremely strong base of semiconductor companies who would be a natural touch point for semiconductor innovation. But we've also got this next wave of semiconductor companies who are more focused on systems and use cases, but who've also built incredibly powerful teams internally. What comes after this? Semiconductors, we now know, and everyone now knows, are so critical. We've got a moment where we can start to draw the attention of all sorts of partners to think about driving emerging use cases, and not just having to climb these very steep hills to be able to create all of the features that need to be supported in today's platforms. And then the third one I've already talked about, so I won't mention too much further, which is that we're starting to see a lot of investment in semiconductors. It goes up and it goes down, and I worry that it'll come down again if we don't ensure its success and convince our investors that this is a rich place to continue to invest in. I think this is a place where fundamental researchers need to get deeply engaged and offer their insights and thoughts so that the insights from fundamental research around where there are major technology barriers and where there are real technology opportunities can also inform the ways that we direct investment. Okay, in conclusion, I just want to leave with the following thoughts. Our strengths across fundamental research and industrial innovation are unparalleled in this country. I do believe we're at a point where semiconductors require highly differentiated advancements, and I think that fundamental research is in a really unique position to contribute to that. The programs that we have in organizations like Netcast really give us a distinct opportunity to establish lasting structures for transitioning fundamental research to innovation ecosystems and ultimately to industrial leadership. There are existing models for this, but I think we need to amplify it even further, and I think we have the potential to do so. With that, I'm going to stop my talk. Thank you.